Now that we've talked about syn additions, let's talk about anti-additions. Where syn additions add the two groups that come in on the double bond to the same side, anti-additions add them to opposite sides, meaning one wedge and one dash. Now, as far as you're concerned, there's really one mechanism you're responsible for anti-additions, because they all essentially start the same way. They start with a dihalogen over the arrow, meaning Br2, Cl2, I2, and all the mechanisms start out exactly the same for that reason. So if you ever see a dihalogen over the arrow, you're probably going to have an anti-addition for your product. Now, how do these work? First off, I'm going to actually draw out the bond because we'll need it in the mechanism. What's going to happen in your first step, there are 3 arrows. 2 of them are pretty commonplace for what we are used to, and the third one looks a little weird from our perspective. The first arrow, the double bond will use its electrons to go out and make a bond to one of the 2 bromines and kick the other bromine out as a result. Those 2 arrows are pretty common. We've seen these before. It's something with a leaving group getting attacked and that leaving group getting kicked out. Here's where the new arrow comes in that gets a little confusing though. What's going to happen is at the same time as this bromine gets attacked by that double bond, the bromine that's receiving that attack will also do its own attack on the end of the double bond. Whether you chose to draw this arrow here or here, it doesn't really matter. It's attacking one of those 2 carbons. The net result will still be the same. And that net result is also kind of weird looking. If we think about it, one end of the double bond will connect to the carbon. The other end is being attacked by the bromine. What we're going to get is a 3-membered ring involving that bromine. This is called a bromonium ion. But let's draw it first, and then I'll write out how it's spelled. So what you get is the bromine being added, connected to these 2 carbons. Now the second you form that ring, you're going to have stereochemistry, because again, you're taking something that's flat, sp2 hybridized on a double bond, and you're getting rid of that double bond. You're making it tetrahedral, meaning now you're going to have wedges and dashes. So whenever you make these kind of 3-membered rings, the bonds that connect to that ring will always have the same stereochemistry, meaning either both wedged or both dashed. For simplicity's sake, I'm just going to draw them both wedged, but keep in mind there's the enantiomer as well. And since these come in on both wedged, that pushes this methyl onto a dash. Okay? Now that bromine, because it has 2 bonds, will end up being positive. It's giving up electrons to make this bond, and in general, when you see halogens on 2 bonds, they will be positive, as weird as that looks. So what we have right here is called the Bromonium Intermediate. Bromonium. Okay? Now, what's going to happen next is the bromine that got kicked out, the Br- that we made in this step, is going to come in and attack that 3-membered ring. So we have a Br-, and it's going to attack this ring. But the question is, where is it going to attack? It has 2 options. It can either attack the higher degree carbon or the lower degree carbon. And the rule is, when you have these 3-membered ring structures where one end is positive, the thing over the arrow that comes into attack will always attack at the higher degree carbon. And so what that means is, for your purposes, this Br- will use its electrons, come in and attack this carbon here because it is tertiary. To make room for this attack, the other bond, this bond that connects the carbon to the bromine, has to be broken. It goes up to the bromine. What we're doing right here is effectively an SN2 reaction, which means this bromine is coming in from the back. It's coming in from the opposite stereochemistry of that wedge bromine, which means when everything's said and done, we will get a product where we have this bromine bond still being their wedge because it was not touched. But on this carbon over here, the bromine had to come in on a dash. And that will push this methyl onto the wedge. Okay? So this is the general mechanism of these anti-additions. The most important thing you have to remember is that you make these weird 3-membered ring intermediates. They will look for they will look to see that you know that this happens. Now, I said this is the base start of the anti-additions and everything just kind of builds off of that. let's talk about some modifications that make this a little fancier. So let's start off with what would be over the arrow to make this different from what it already is. The key difference that you'll see is instead of just giving you a dihalogen, they will give you a dihalogen in some kind of solvent. For example, water. Well, if our dihalogen is mixed into a solvent of water, the first step is still exactly the same. The double bond goes and attacks one of the two bromines and kicks the other one out, and the bromine that received that double bond's attack will come in and attack one of the ends of the double bond, giving you this three-membered ring intermediate again. Here's where things start to differ though. What's going to come in after this ring is formed? Well, we have an option. We have the single Br- that we made in that first step. But keep in mind that Br- is just one, and it's dissolved in a solvent of water. If water is your solvent, that means there are thousands upon thousands of molecules of that water surrounding the Br- and your current intermediate. So in terms of probability, what do you think is more likely to happen? A Br- coming in or the H2O? Hopefully you said H2O because there's just simply more of it. So what's going to happen now is the H2O is going to come in and attack one of these two carbons that connects to the bromonium ion again. And what did we say before? Where will it attack? The higher degree carbon. So that H2O will use its electrons, go and attack the higher degree carbon of that three-membered ring, and break the bond going to the bromine. So what happens is instead of adding a second bromine, we're adding H2O. And that means we'll get nearly the same product, but instead of two bromines, this bromine that got added to the higher degree is now H2O. More specifically though, it comes in as H2O positive. Why? Because we didn't remove any of the hydrogens through this mechanism. That means that oxygen should still have all of its hydrogens. And since that oxygen has three bonds, it gave up its electrons to make this bond happen, it's going to be positive. So we have one last step. We need to deprotonate that OH. And all we need to do that is just have another molecule of the solvent come in and pull off that proton. So one more molecule of water will come in, grab one of those two hydrogens and put the bond electrons onto the oxygen, giving you the final product, which would be the six-membered ring, the leftover wedged bromine, the wedged methyl, and the dashed OH. So the long story short of this reaction is you put the OH on the higher degree, the bromine on the lower degree, and they should have opposite stereochemistry to each other. And we're not limited to H2O as our solvent. We could use something, for example, like CH3OH. But the mechanism and the concepts are still exactly the same. The first step, you have this dihalogen over the arrow, and you do your three arrows where you form a bromonium intermediate. Then instead of the OH of an H2O coming in to attack that bromonium, it's the OH of the CH3OH. So this oxygen would come in, attack the higher degree, and break open the ring. And so in this step, instead of having H2O positive, you'd have CH3OH positive. And then instead of H2O deprotonating it, another molecule of CH3OH would deprotonate it. So it's still the same exact idea. You just would get an OCH3 with a bromine anti to it. Now there's one more variation of this question that I see used quite often, and it's probably the most challenging of the bunch, but it's definitely worth going because of how popular it is as an exam question. So let's take a look at this. Let's say you are given a six-member ring like so. And off of that six-member ring you have a double bond, and then something that looks like this, carboxylic acid, carbonyl with an OH on it. And over the arrow you're going to be given two things. You're going to be given NaH, and you're going to be given Br2 again. Okay? So half of this should be familiar. We see a dihalogen, and right now the only thing we know dihalogens do are those weird anti-additions. NaH, on the other hand, what does that do? Well, we know for a fact that whenever we see sodium coupled with something, we know that it is a metal. So sodium is positive, and whatever it's attached to must be negative. So we have H minus. H minus is a super, super strong base that loves to take protons, especially off of OHs. And that's exactly what's going to happen. The first step of this mechanism is your base will pull off a proton from this OH. So this hydrogen uses its electrons to take that proton. Let's draw the bond. It'll take this proton, and the electrons swing onto the oxygen. And now you have the same six-membered ring, the same double bond, but now you have this O minus floating around. And that's about it for that NaH. That's all it's doing in this reaction. So now we're left with just the Br2 to worry about. So now we're going to bring in that Br2 over our arrow and do what we did before with it. Have the double bond do those three arrows, meaning the double bond goes out and attacks one of the two bromines, the other bromine's bond breaks and kicks out that second bromine, and then the bromine that received the initial attack goes and attacks the end of one of the double bond's carbons. And so we're going to get that bromonium intermediate again. So our six-membered ring, this group that we got deprotonated in our first step, and now at the same time we're going to have our bromonium ion three-membered ring. I'm arbitrarily choosing to make this wedged. I could have made these both dashed. What's important though is to realize that if these are going to be wedged, this methyl will get pushed onto a dash like that. Now what's going to happen after that is interesting. We have two options. We have the Br minus that we kicked out that could come in and attack here, but there's another possibility as well, and this is a possibility you have to be on the lookout for. For exam 2, we taught you the concept about intramolecular reactions. The concept that if you have in your molecule a good leaving group and a good nucleophile at the same time, the molecule will react with itself rather than whatever's floating around in the solvent. Because having a reactant right next to its neighbor is much faster to have those two react than something floating over here in the solvent that has to hit it at the right angle, at the right energy, at the right time. So having this O minus floating around, this good nucleophile floating around right next to the bromine at all points in time, makes it very easy for these two to react much faster than the Br minus we kicked out in that first step. And that's exactly what's going to happen. This O minus is going to attack one of these two carbons. Now, normally we say the thing that comes in and attacks this ring adds to the higher degree, but there's a reason why it's not in this case. Consider what would happen. If this oxygen were to attack here, well, we'd be forming a ring, right? We'd be connecting that carbon to that carbon. We'd get a 1, 2, 3, 4-membered ring. And we've taught you that 4-membered rings are super unstable. On the other hand, if this O minus were to attack this carbon and break that bond, well, we'd be connecting 1, 2, 3, 4, 5 carbons. We'd make a 5-membered ring, which is stable, which is very favorable to form. So that's what's going to happen. It's going to choose to make the most stable ring. And so that O minus comes in and attacks here, the bromine gets kicked out, and you're going to be left with this as your final product. That dashed group, the carbonyl, the oxygen. That oxygen is coming in from behind this wedge, which means it's going to be attached on a dash. The bromine that didn't, so this bond broke, the bromine is no longer connected to this carbon. This carbon, however, kept its bromine bond, and that bromine is on a wedge. And so this would be your final product. This is hands down the most difficult question from this chapter, or the most difficult mechanism, just to visualize and understand. So it's super important you get it down because that's why they favor it so much on exams. It's a challenging problem. You'll usually see something like this in recitation or on a past exam. So make sure you go to your TAs and ask questions if you're not fully clear on it.